that host headers, validating host headers might be an adequate form of defense against anti-DNS pinning attacks. Let me be very specific. Host headers are not security. There have been several vulnerabilities in the past with both Internet Explorer and Firefox that allow an attacker to arbitrarily set the host header for new requests. Now, these bugs have been patched, but there's no reason to believe that all browsers have installed those patches or that similar vulnerabilities won't be found in the future. And in fact, there is a similar vulnerability in Flash. But there's plenty of default websites that are on the internet, and there's even more that are on internal networks. Even if the attacker is unable to find a default website, you still could use a method such as a buffer overflow attack against the web server. Something complicated like chunked encoding is not possible with XML HTTP request, but something with a overflow from the URL or in a header that JavaScript is allowed to manipulate could be launched regardless of the default website state. More likely, though, the attacker would browse the network, look for a long-forgotten, rarely used web application that I'm sure all of us have back at work. It's probably written by junior developers, riddled with SQL injection flaws. And if the attacker is lucky, the backend database will have a tertiary vulnerability, such as XP command shell, that could allow the attacker to set up a more traditional and flexible tunneling method. However, if Java is enabled on the browser, then more sophisticated attacks become possible. Before I go into much detail on that, let's do a quick refresher on Java security. There's two kinds of applets, a trusted and untrusted. A trusted applet is either digitally signed, much how ActiveX controls are, or it's installed locally. The trusted applets have pretty much the same level of privilege that the user does. They can access the file system, read, write, create, delete, the whole thing. They can create and terminate processes. And they can have unlimited network access, either outbound sockets to any server or even acting as with a listening socket. Everything else is considered to be untrusted. Untrusted applets have no access to the local file system. They have no process management capabilities. And the only socket abilities that they have are outbound to the origin server, but they can connect to any port on the origin server. Now, the JVM performs its own DNS pinning, and as a result is not going to be vulnerable to the same attacks that we were launching against the web browser. As I mentioned at the beginning of the presentation, the first anti-DNS pinning attack was documented in '96 against the JVM. And what the researchers noticed at Princeton was that if DNS returned two different IP addresses for the origin host name, that Java would consider either one of them to be an acceptable destination for outbound sockets for untrusted applets. Sun addressed the problem pretty quickly and said that in the future, the applets would only be allowed to connect to the actual IP address that the applet file, the class or the jar, was downloaded from. Now, I don't have a 10-year-old copy of Sun or of Java, so I can't say exactly how they implemented it at the time, but as you'll see in a little bit, that is not the behavior that the JVM exhibits today. The Princeton attack, again, was very similar to a general DNS rebinding attack. Browsers convinced to go to a malicious website. The browser could be performing perfect DNS pinning, keeping it in its cache. The attack web server responds with HTML that contains a reference to an applet, and that causes the browser to initialize the JVM. One of the first things the JVM does is send its own DNS query back to the DNS server controlled by the attacker. The DNS server responds with two IP addresses, which the JVM pins in its cache. JVM takes the first one and connects that back to it, which is the attacker server, downloads the applet, and the applet sets up a socket connection to the second IP address, which of course is the victim's server. Because both of those came in the DNS response, the JVM considers it to be acceptable and not a violation of same origin. Now, that attack isn't possible anymore, although some variants are. A more effective attack using a technology called LiveConnect is possible. LiveConnect is essentially a bridge between Java and JavaScript that Netscape introduced. It allows Java applets to interact with the document object model on a page so that it can create new content, change attributes, things like that. And more importantly, it allows JavaScript to instantiate standard classes that are part of the Java distribution, including sockets. It's only supported by by Firefox and Opera, not by Internet Explorer. So this next demonstration won't work against IE, but there are some similar attacks that I'll talk about that will work against currently any browser that's using the JVM. Earlier this year, Martin Johns and Kanatoko Anvil documented that if JavaScript creates a Java socket object back to the document's origin hostname, that, of course, the JVM is going to immediately query DNS. However, since there's no applet file to download with Live Connect, this query is for DNS pinning only, which means that the DNS server can respond with whatever IP address it wants, and the JVM will connect to it. So there's a number of advantages with this. There's no delay that's caused by waiting for the DNS pinning to time out. Because we have direct access to sockets, the host header restriction is limited. We can just craft our own HTTP request from scratch. But more importantly, pretty much any text and binary protocol over either TCP or UDP are supported. There's even limited ICMP support. This has huge potential. Telnet, SSH, SSL, SNMP, database server protocols, NIS, CIFS. The vast majority of traffic tunneled over, or excuse me, transmitted on a network can be tunneled through Firefox using this method. My demonstration, the environment is very similar to the first one. A few exceptions. Instead of an HTTP proxy, a SOCKS proxy is used on the attack server. For those of you who aren't familiar with it, SOCKS is a protocol that lets pretty much any TCP or UDP protocol be tunneled through a proxy server. The attacker's workstation has a generic SOCKS client bound to the IP stack so that any request that's sent to a 10-dot address range is redirected to the SOCKS proxy. Again, there's no need for a firewall change. And the reads and writes from the sockets can be handled more or less asynchronously using the kind of pseudo-threading that JavaScript supports with set timeout. So let's get started with this demonstration. And let me clear up the environment from the first one real quick. And this time, I'm not going to be doing the fakenews.com. I think that the point was made pretty well. So it's registering itself again. We can test that traffic is flowing properly by sending arbitrary JavaScript. And the attacker can start the SOCKS proxy. The first traffic that we'll send is just going to be a simple Nessus scan. As you can guess, this is going to be a very targeted scan. While this is a powerful tool, it's not as fast as direct access, and watching Nessus run is not very exciting. One of the things that makes this technique so powerful is that once an attacker has access to the internal network, simple tools can be used. It's not even and internal networks are usually not nearly as well secured as the corporate or internet environment. If we switch over to the victim side, you can see that a new iframe has been created. This time it's for a SOCKS connection, the random host name and the IP address. These are the image placeholders for the data being sent back to the attack server. And very similar setup for data being posted back. You can see it changing. It's basically just an array of byte as more data is being sent. If we go back to the attack side and take a quick look at the packet capture, you can see that it's being identified as SMB traffic, which is fine. I'm not cheating. It starts off with a SOCKS handshake, and Wireshark is smart enough to recognize the protocol that's being tunneled, which is SMB in this case, and it's still going over 1080, which is the default port for SOCKS, and it's still all between the attacker's workstation and the attack server. So the scan should be getting pretty close to being done by now. Here we go. As you can see, not surprisingly, the server is not very well maintained by the administrators. And this is just using a few plugins for Nessus. We were able to get some reconnaissance out of it as well. It's running Windows 2003. So at this point, we can launch an attack. And again, this doesn't have to be with anything fancy. Something as easy as Metasploit can be used. And we'll be launching just a simple RPC attack. There we go. The payload that I'll be using is just going to be a simple simple shell bound to a TCP port. Normally, an attacker would probably be using a reverse shell, which would cause the victim server to basically phone back to the attacker over the internet. But because it takes a little bit longer to set up, so I'm going to be using just a straight shell. It'll be a little bit slower since it has to go over the SOCKS proxy, which is why an attacker probably wouldn't use it, but it's faster for just a short demo. All right, and if we switch back to the victim side, you can see traffic coming in. The first thing that Metasploit does is check to see if there's anything listening on port 4444, which is where the shell is bound. There isn't, so Java basically detects that just by throwing an exception. And let's see, it's going to have to launch again. So traffic's coming through. All right, switch back to the attacker side. And always seems slower during the presentation. Here we go. Have a shell. This is basically with root level access, system level. We can show that by just quickly going into the administrator's directory, desktop, switching back to the victim. I'm going to move over to the victim server. This is just the administrator logged in to his desktop. There we go. Just send something really quick. And there we go. So, system level root access from the internet to a private network all over Firefox. Okay. As I mentioned, this attack only works on Internet Explorer, but I'd be willing to bet that the vast majority of us use Firefox as our primary browser, perhaps maybe not with Java enabled. There are a few other techniques, though, that will work against Internet Explorer. Last month, I documented that 3 of them. The first one's not really a new attack per se. Turns out that the Princeton method is still possible when the victim server, the victim web browser, and the attacker server are all on the same subnet. Now, this isn't an extremely useful technique, but it is revealing about how DNS binding does or doesn't work in Java. The second method is a little more useful. It's also based on the Princeton method. If DNS returns 2 IP addresses, the JVM will perform reverse DNS lookup on both of them. If the results match, if the pointer records both have the same host name, then the JVM will consider both addresses to be acceptable for the origin and allow a connection to continue. Normally, an attacker isn't going to be able to set or control the reverse lookups for a private IP address range, but there are a few scenarios where that might be possible. If the attacker had compromised